So I'm Dan Turner. Thank you for joining in, and I have the title as Remove Mysteries of Accumulators for Safe, Efficient Design. That just sounded a little better than saying fun with accumulators. So we're going to have a pretty basic discussion today. I don't know the experience level of everyone that's tuned in, so hopefully we appeal to a little bit of everyone. So accumulators, what are they? Well, an accumulator is the hydraulics as a capacitor is to electronics. A capacitor and an accumulator both are energy storage devices and can also be used as surge suppressors. So most modern accumulators are gas charged, though in the early days they were weight loaded accumulators, which would store energy with a weight put on top of the piston that was inside of a cylinder. And this mechanism would provide a consistent oil pressure from the accumulator until the piston would hit the bottom of the chamber. The gas-charged accumulators today, they do not provide a constant pressure as the weight-loaded accumulators did, or still do in some cases, but they drop in pressure as they discharge fluid. Again, very similar to a capacitor. Gas-charged accumulators have a barrier between the gas and the fluid. So there's three main types of gas-charged accumulators. You've got your bladder, diaphragm, and piston. The most common gas that is used is nitrogen. It is always an inert gas. So nitrogen is the most common. So on the left, we've got the bladder accumulators. You can see the components that are involved there to make up a bladder accumulator. The first thing, which is the most obvious, is the shell. And then you have the rubber bladder that's inside of that. And at the top of the bladder, there's a stem that is used to hold the charging valve and the gas valve. Then at the bottom of the accumulator is a poppet, which keeps the bladder from extruding out through the oil port, and a little bit of a spring there on the poppet. In the middle, we have the diaphragm accumulator, which is the simplest accumulator, really. It has the shell, a charging valve, and inside there's a diaphragm, and then just the fluid port there at the bottom. At the bottom of the diaphragm, there's generally a button, and that can be a hard plastic button, and that's what keeps the diaphragm from extruding out through the oil port. On the right, we show a piston accumulator that is generally made in a cylindrical body with, it has a gas cap, it has the hydraulic cap, and then there's a piston in the middle, and generally the pistons will have a hollowed out part to them. And the hollowed out part is generally always to the gas side. So whenever you take these things apart to repair them, make sure you get that piston in the right direction. So a piston accumulator's a very simple design as well. And the key there is that there's seals on the piston that separate the gas from the oil. Just as in the diaphragm and the bladder, you've got the rubber membrane that separates the two fluids. So here's a cutaway of a bladder accumulator. On the top, we've got a protective cap that goes over the gas valve. You can see the bladder inside of the shell and the poppet, and below the poppet there's a spring that in the natural position will keep the poppet off of the port, but whenever the bladder is filled with gas, it pushes the poppet down against the seat in the oil port. And below the poppet there is the AER, the anti-extrusion ring, which gives the bladder a nice smooth base and is the retainer for the oil port. So each type of accumulator has unique features. One of the critical determining features of which accumulator to use is often the cost to manufacture, though no one style is best for all applications. So accumulators can range in dollar amounts, and that's one of the determining factors that people use as to determine which one they're going to go with. Accumulators are pressure vessels. So they are regulated by each country and where they are used, not the country of manufacture. You can have it manufactured in one country to meet the specifications for other countries in which they will be used. So whenever we talk about this, the U.S. recognizes ASME certification. So that's the most common in our territory. Canada is CRN, and Europe uses the CE, which is, by the PED. So the one of the things to consider when ordering is to make sure which certification is going to be the ruling jurisdiction over where the accumulator's going to end up at. So let's talk about the different types here. We've got the diaphragm, and they just look like little bombs. They feel like it too. They're just a heavy piece of metal, and very nondescript, you might say. They're generally the smaller size capacity of accumulators, and you rarely see these over 1 gallon, and rarely even do you see them being a gallon. They can be repairable, where they thread apart, but there's a lot of them that are also non-repairable. And these are generally readily available, which leads into why you might pick a diaphragm accumulator, and they're great for mobile applications. We have bladder accumulators. These are generally the next size from your diaphragms, but they do range from 1 pint to 15 gallons as the most common sizes. Bladder accumulators are repairable, and they are readily available. So you can generally get bladders and diaphragms right off the shelf. The specific sizes range from your 1 pint to your 15 gallon, and there's very specific increments there. It's to ask for an 8 gallon accumulator is not going to happen in most common accumulator sizes for the bladders. Bladder accumulators come in different pressure ratings. So the diaphragms can be a variety of pressure ratings, but with bladder accumulators, there's certain pressure ratings that are expected, and that's the very common common practice. You have 3,000 and 5,000 PSI accumulators. Now you can increase basically that same shell from 3,000 PSI to 4,000 if it is certified using the Appendix 22 certification. And as well as the 5,000 could go to 6,000. So if you're working a system and you're just a little over 3,000, you might be able to save some money and save some weight, go with an APP 22 instead of going up to a 5,000 PSI accumulator. So on the pressure ratings, you also run into the difference in the gas valves that will be used to fill the accumulators. I've got a picture on the right-hand side there, and the two on the left are 3,000 PSI gas valves, and you can see that I've pulled the inserts out, and that's the common method for that. The two on the left are very similar, except there are different thread sizes where they screw into the bladder stem, and that's important because you can't just always plan on buying a gas valve from one manufacturer and having it be able to be used on a bladder from another manufacturer. So whenever you buy a bladder kit, just make sure you've got the matched gas valve. On the right-hand side, we've got 5,000 PSI gas valves, and they're both the same, but on the right-hand unit, you can see that the poppet is extended down past the threads on the bottom where it would thread into the gas stem. And so that's how these are operated instead of an insert. The hex on top is rotated, which extends and retracts the stem inside. And on the one second from the right, you see that that stem is up tight, so that is a metal-to-metal seat, and that is what locks the gas inside the bladder. The one on the right-hand side has been opened, and the gas now can come out of the bladder, and you can charge it. The gas valves on the left with the inserts, they act like one-way valves, so you can just pressurize those, but generally you'll be depressing the stem. On the right-hand side, you can't get any gas in or out unless you unseat that stem. With the bladder accumulators, not only do we have the different pressures, but we also get into what convenience configurations, and I call it that because we can have top and bottom repairable accumulators. The top repair style allows us to service the unit while it's in place on the machine. You have to make sure you've got a safety lockout, that you can isolate the energy from the system, but once that is done, you can actually replace the bladder without taking the accumulator off of its mounting and without taking it off the port. So it's generally much more convenient to replace a bladder in a 15-gallon accumulator while it's still in place. You're talking 300 pounds for a 3,000 PSI unit, like 500 pounds for a 5,000 PSI. So you really don't want to be lugging those around. But then when it comes to maybe a 1-gallon unit, they don't come with top repair, so it's not that big of a deal to be able to take a 1-gallon off of its mounts, repair it, and put it back. Now, why would you go top or bottom? Convenience is why you would go to the top. The bottom is least expensive, and generally they're, say, at least 20% less whenever you go to a bottom repair than a top repair. The third type of accumulator is the piston style, and these can be small units or they can be as large as economically feasible. They can be any volume. So like your diaphragms are always relatively small, and your piston or your bladders come in specific sizes. The pistons can range in any size that you possibly need, and because they're manufactured generally to specs or to order. So almost all pistons are repairable, but then you get into some of the smaller units that are actually welded and sealed. Some aren't welded, but they're just crimped at the ends and sealed. Very inexpensive. So your piston accumulators can run the gamut from relatively low cost to major expenses, and they can go from small to large. Pistons are less tolerant of contaminants. All you need to do is get a piece of dirt against the piston and the tube wall. Once a scar is in the wall, you'll never be able to seal that up again. So you need to keep the oil relatively clean. Nice thing about pistons is that they can be mounted in any position. It really doesn't matter which way you're going to have them laying, and often you'll see them horizontal. A real nice feature is that they're very conducive to having remote gas bottles. So you can see in the picture on the right that there's only 2 accumulators here, and the rest are banks of gas bottles that are actually feeding into the top of those piston accumulators. So it really helps you to increase the amount of oil that you can get out of an accumulator whenever you can have remote gas storage. One of the problems with piston accumulators is that they can have long lead times. So whereas we've got the diaphragms and bladders that you're getting relatively quickly, the pistons can take months to manufacture. Mounting of accumulators. Piston and diaphragm accumulators may be mounted in any orientation. They're really not affected by which position they're going to be. Horizontally mounted bladder accumulators can suffer from premature bladder wear, as well as have their volume derated as oil can get trapped inside. And if you think about it, if you took a bladder accumulator and turned it upside down to where the oil port is up and the gas is down, the oil is heavier than the air, and the bladder is going to want to try and float on top of that oil. So you can see that the bladder would go up and shut the poppet off relatively quickly as soon as you started to discharge oil out of the bladder accumulator. So I like to exaggerate to that point and say the more you would turn the oil port from pointing straight up to pointing straight down, the better chance you are at being able to utilize all the oil that's inside that bladder accumulator. So even when you have a bladder accumulator horizontal, you have the chance that the oil is going to lay on the bottom, and at a certain point of discharge, the bladder will actually close that poppet, and you're going to trap possibly a third of the oil inside of the accumulator and wonder why you're not getting the performance that you expected. On pre-charge of accumulators, bladder accumulators should not be charged less than 40% of the maximum system pressure. This is a fairly important fact to know, is that the bladders will not handle the deformation that is caused by having too low of a gas pressure. The bladder gets pressed up against the gas valve port, and it will actually pick a hole in your bladder, and at that point you've just compromised the bladder. The gas is going to leak out into your fluid system, and when that happens, it can be almost catastrophic with a very fast release of high pressure gas. So you like to make sure you're keeping your bladders pre-charged properly and don't let them get too low. Diaphragm accumulators are nice that they can go down to like 20% of the system pressure before you would expect to actually cause a failure in the diaphragm due to low pre-charge. Piston accumulators, on the other hand, can go to a very low pre-charge with no premature failure. There is nothing there that's being distorted. You're just moving the piston inside the barrel. So there's not a problem as long as you're not creating the piston to slam against the end too much. It'll handle a fairly large pre-charge to system pressure ratio. Response time of accumulators. Bladder and diaphragm accumulators, they're very fast responders. And they're not moving very much. They've just got that bladder that's like spring-loaded, ready to push the oil out as soon as it can. Piston accumulators can be pretty fast. They respond within 25 milliseconds. It's still not as quick as what bladders and diaphragms are, which are basically instantaneous because they don't have any seal stiction on the pistons or the piston mass itself that needs to be accelerated. So the bladders and accumulators can work very well for absorbing spikes and for feeding fast-acting servo valves. You may not want to consider using a piston accumulator for some of those applications. Flow rates of accumulators. Your standard bladder accumulators should not exceed 220 gallon per minute. And I say standard because there are high flow bladder accumulators with larger ports, and they're made to be able to handle the larger gallon per minute. But if you exceed that, it's possible that the poppet can actually be prematurely closed, and you're going to be shutting your flow off. So piston accumulators are not limited to the flow rate, but more to the piston velocity, and they generally do not exceed 10 feet per second. So if you said you wanted a lot of gallon per minute out of a piston accumulator, you may go with a larger diameter so that you don't have to have your piston traveling too fast, but you still get the large volume out. Cost of accumulators. Your diaphragms can be very low cost. Your bladders are generally not quite as low. And your pistons, as I had mentioned earlier, they could be welded or are basically crimped together, so they can be a fairly low-cost unit as well, and they can go up to substantial dollars. So, you know, that helps in making the decision sometimes as to why I should use a bladder accumulator, maybe, because the diaphragms and bladders are really the best value if you're strictly looking at the volume per dollar. But there's sometimes whenever you just, maybe you want to use remote gas bottles, so you may not be going with the bladder for that, or you need a size larger than what the bladder is going to handle, and a variety of reasons why you would go away and use a piston. Technology integration. So, you know, things are really moving towards being able to incorporate technology into a lot of fluid power systems today. Diaphragms and bladder accumulators are relatively boring. There's not a lot we can do with those. You can do gas side pressure monitoring. You can put transducers on the gas side, or permanent gauging systems. And you can also use a variety of shell and bladder materials to be able to handle different types of fluids, but that's about as exciting as it gets with bladder accumulators. Piston accumulators can be fitted with all the above, as well as piston monitoring systems. And the systems can be LVDTs or discrete piston position sensors. So on the left, we show where it's a discrete piston position sensor, and they're able to sense from outside of the shell to where the piston is whenever it passes in front of the sensor. So it's only telling you if it's there or if it's not there or if it was there, but it's not telling you where it is currently if it's not in front of one of the sensors. So on the right-hand side, we actually show one that has a string pot internal, which is connected to the piston, and that piston is able to go up and actually surround the string pot without damaging it. So that can be, the string pot can be fed outside with a cable, and you're able to determine the position of that piston no matter where it's at inside the tube. And there's other ways to do it as well. You can use the string pots, you can use ultrasonic sensors, IR, and you can use LVDTs. One of the things about LVDT rods is that generally you're going to have a magnet on the piston, and then the piston has to have another seal on it that is going around the rod. So you've got now two different leak paths for the gas and oil to mix. You've got your regular piston seals as well as the LVDT rod seal. So it's nice to be able to use something like a string pot or something else that's not really penetrating through the piston. Fluid compatibility for accumulators. They can be manufactured to meet the compatibility requirements of almost any fluid. Shells and tubes can be carbon, stainless steel, composites, or it can be a carbon steel that's coated to be able to handle specific fluids. Bladder and diaphragm seals can be Buna, Buna-N, EPR, Viton, butyl, or hydrogen. They are the most common types of materials for the bladders and diaphragms to be manufactured in. Piston seals are very similar with the same selection, but they can also be made from other compounds or polymers. So in some cases, a piston accumulator is going to handle the compatibility issue with fluids better than what your bladders or diaphragms can. So that's another reason for pistons. Here I have just I borrowed some slides here from the International Fluid Power Society. This is an animated schematic, and as long as I can get this to work, if I can get my mouse to show up here, I'm not sure I've tried this yet. There it is. Okay, so we're just going to show that we've got a pump that is going to be flowing across a dump valve, and what flows into the dump valve, fills the accumulator. Sorry about that. All right, got to figure out where this is at. So I want to stop this at a certain point. And unfortunately, when I go to stop it, it indexes me to the next slide. So what I wanted to show was that the accumulators are governed by Boyles Gas Law. And that is very simple, simply put as P1 times V1 is equal to P2 times V2. So the pressure, the initial pressure times the initial volume is equal to the pressure at some other point as well as the volume. So whenever we're starting off, our accumulator is generally empty of fluid but full of gas. So we take the pressure of that gas, which we refer to as the precharge, we multiply that by the volume of the gas, and that gives us the first part of the equation. And then once we charge the accumulator, which is what I was trying to show, is that we would compress that gas to half of its original volume, which would be our V2, and we would create a certain pressure inside of that accumulator that we can solve for. That's not normally what we're trying to solve for. We normally are trying to figure out what amount of, what size accumulator we need to do a certain amount of work, but that is basically the formula that you can use as long as the oil and gas stays at a constant temperature. It's a very good basic formula. So on the right-hand side, I've just shown a little bit of math there. If we had a 10-gallon accumulator and it was empty, and then it is full of 10 gallons of gas, and if we precharge that to 1,000 psi, our number there is 10,000, which would be equal to whenever we compress the gas to whatever our let's say our system pressure is going to be. And if we are able to put into that 10-gallon accumulator, if we put 5 gallons of oil into that, we've now decreased our volume of gas from 10 gallon to 5 gallon. And whenever we do the math to solve for that, we can see that our pressure of gas will go up to 2,000 psi. So it's a very linear equation, and you can see that the pressure and volume are basically inversely proportional. So as the pressure, as the volume is increasing, or as of gas is decreasing, the pressure is going up equally proportional to that. So an important thing to think about whenever you're doing these calculations is notice that it's Boyles Gas Law. So whenever you're calculating this, you're actually calculating the gas volume. And there's mistakes that are made sometimes that people don't then do the math and finish the equation for the amount of oil that's going to be discharged out of the accumulator. So make sure whenever you're working the gas law that you actually finish and account for the oil. So I'll just go ahead and start this up. You can see that it's running up across, filling the accumulator. At a certain point, this is an accumulator sensing pump unloading valve. So when the pressure goes to a preset point that was dialed in or on the dump valve there, the pump unloaded, and now we've shifted the valve, driving our cylinder out. We're doing a lot of work here, but as we're doing that work, the pressure is dropping inside the accumulator, and therefore we aren't able to attain, let's say we were using that 2,000 psi, we weren't able to keep the system moving at 2,000 psi. And with retraction, maybe we don't even need close to 2,000 psi, but maybe only 1,000 psi. At the end of this, our cycle is stopped. Our accumulator can recharge again. There we go. And then at the end of whenever you shut your machine down, you've got a dump valve that will eliminate all the energy out of your system. So there's a couple important things here. This is a real nice circuit because it uses, just a hydraulic valve to be able to unload the pump once the accumulator gets up to pressure. You can buy those valves with different setting ranges, and they're adjustable. So maybe you want it to unload the pump whenever you get to 2400 psi. You can dial that in. And the cartridges that you can buy to do that with generally come in a percentage of reset. So you can buy them for like 15% reset, even up to 50% reset. But that reset percentage is not settable. It's just the pressure at which it's going to unload the pump. But it's a very nice, convenient way to do it. Another thing I'd like to point out is that in between the accumulator and the system unloading valve, solenoid 1 there on that 2-position valve, there's an orifice. And it's important to make sure you've got an orifice in between your accumulator and your reservoir, because if you dump all that accumulator flow at one shot back to the reservoir, it's possible you're going to compromise the reservoir end seals, or it just creates a tremendous shock very quickly back to your system. So it's always nice to have an orifice to control that discharge. And as well, there's flow controls on both sides of the cylinder there, because you want to make sure that the accumulator doesn't just radically discharge into that cylinder. You want to be able to control the discharge of an accumulator. You can also put a flow control, and it's very common to put a flow control after the accumulator. But in this case, they wanted to control the different reactions of the cylinder separately. Here's another animation. And this one uses a pressure switch, which is on the left-hand side, to control an electrical dump valve. There we go. Got to find where my mouse is at. And again, this is contributed from the International Fluid Power Society, so I'd like to thank them for letting me use this. So the pressure switch is what's going to be changing this over. And one nice thing about pressure switches are, once you've got electrical in the system, you can now be sending signal to say machine ready. You can also change that pressure switch to basically anywhere you want. You can use a high-low pressure switch so that you can change your delta P on when the accumulator is completely filled and when the pump needs to start back up again. And notice that in all these scenarios, the pump is also providing oil as well as the accumulator in the sequence of operating the cylinders. So as long as you don't need more, or as long as your cylinder requires more pressure than your accumulator, you will put your pump's oil into the cylinder. If at any time it takes more force to move the cylinder than what the gas pressure is in the accumulator, you will then start filling the accumulator before the cylinder moves again. So that's just one thing to consider on your design systems. I put a little note off to the left that says you can determine the precharge of an accumulator by watching the gauge whenever you discharge the accumulator to the tank. So if we had a gauge on this circuit, and if the gauge were very close to where the accumulator is, whenever we operated the valve on the top right-hand side, that 2-position normally open valve that is now shown open, let's say that we had a gallon of oil in that accumulator. As the gas is pressing the oil out of the accumulator through that orifice, through that 2-position valve and back to tank, the gas pressure is going to be dropping. And we would notice that our gauge that's on our oil side is very representative of the gas pressure in the accumulator. At the point that, let's say the pressure inside the accumulator is at 1,000 whenever we first start dumping it, and we notice that the needle is dropping from 1,000 to 900 to 800 to 600, and all of a sudden it goes from 600 to 0, like instantaneously. At that point, we know that the gas pressure inside the accumulator is very close to 600, because it's maybe at 625 psi, and then one more drop of oil is the last drop out of the accumulator. And at that point, the accumulator no longer has any effect on the system because all the oil was out of it. So the pressure drops instantaneously. And that's just a fairly crude way, but in some instances, that's a good way to be able to determine what your precharge, or at least that you've got a relatively good precharge in your system. So if you don't know what that is, you should document that with your machine or somewhere in your maintenance records, and be able to tell what that is. Another point of knowing what precharge, when you're having a problem with precharge, is the cycles of the machine. You should be able to document your cycle time when you know that everything's working properly, and then you'll be able to tell whenever you're starting to have a problem. We had an instance a couple years back where an amusement company had a ride that had safety restraints that had accumulators on them. And one of their things was that they needed to have the accumulator charge tested periodically. And the problem was that after they checked the accumulator pressure probably 3 or 4 times, they found that their pressure was low and they needed to refill them. We worked with them and said, you know, every time you check them, you're taking some gas out, and these are relatively small accumulators. So let's come up with another system, another way to tell what the precharge is. And they were able to work with the factory, who is the one who devised the procedure to begin with, and they revised their procedure so they were no longer having to tap in and check the gas charge and disperse gas every time they check the accumulator. So there are ways that you can do this, especially with small accumulators. You might want to be able to figure that out before you're constantly going in there, engaging the gas and releasing it to atmosphere. Hopefully that makes sense. So in some systems, it's more efficient to actually gauge it. Some systems, it's better to come up with an alternative method to make sure you've still got the integrity in your accumulator. So different applications for accumulators. They can be energy storage devices and you know, used for energy efficiency. And in today's world, I think accumulators have many more applications than what have really been explored in the past because of the energy efficiency that we're really requiring out of our machinery today. They can be used for energy storage for safety and security systems. And they can be used for surge suppression. So we want to talk about energy efficiency. An accumulator can receive and store pressurized fluid during low flow requirements for a process. I've seen some pretty extreme examples of this. And in one instance where you've got like a 1 gallon per minute pump filling a 2.5 gallon accumulator, but it might take a little while to do that, and you can see that actually it'd be over a minute. But whenever you need that high flow of oil to be able to do maybe one part of a production cycle, you can release up to like 100 horsepower worth of fluid in a fraction of a second. And one of the things that uses this principle are hydraulic launch systems. And even in amusement parks, you'll see some hydraulic launches on coasters that they have, let's say, you know, 2 or 3, maybe 5 minutes to build that charge in the accumulator, and then it's all dissipated maybe in 10 seconds. So they've got that ability, instead of having huge horsepower, they're able to figure it out with a fraction of the horsepower actually required. Here's a system that we worked with years ago. It's actually a lift for the Ford Motor Company that they used at the Detroit Auto Show and took like 12 people at a time up into and rotated them in this what they called the cloud experience. And so guess I've been talking for a while. That was my timer already telling me I should soon shut up. So anyway, what we did here was we looked at it and we talked with them about how they could achieve this. One of the problems was that on the convention floor shows and in a lot of places where entertainment is setting up in an arena or something like that, there's not a lot of power that you can use. So sometimes you're limited to like a 15 horsepower electric motor that you've got to be able to achieve certain effects with. And in this case, that was the case. The case. And so we looked at this and we had to look at what it was they were trying to do and what amount of time we had to be able to do it in. And we identified when there were high flow instances required, when there was low flow required, and when there was no flow. And then we were able to look at that and figure out how much time we had to do anything in. So we knew that we needed the maximum flow and the maximum pressure to be able to do the lift. And then we needed just low flow and low pressure to lower it down. And there was no flow required while they were up rotating in the cloud experience, as well as no flow required while we were loading and unloading people. So we knew that we had a certain amount of time to be able to be building and storing the energy in these accumulators. We ended up using 12 5-gallon bladder accumulators, and they had to be relatively small and everything had to fit underneath that stage. But we were able to use those different points through the cycle to be able to make everything work. So even while the people were up rotating, we used that time to recharge the accumulators as well. And we knew when they were coming down, we weren't using as much oil. So a lot of the pump flow could go towards the lowering process and not really use the accumulators. So it's pretty amazing. Plus, you can also do something like that without very much noise because you're using a relatively small motor instead of a whole bunch of motors to, be able to pull that off. We also use accumulators for storing energy and safety and security circuits. So they can be used on clamping circuits whenever you're actually holding a workpiece or something to keep it from being able to break loose. And that's one instance where you'll use accumulators on working ports, which isn't always the most common. And sometimes putting an accumulator on a working port is actually inefficient. So before you go putting an accumulator into the system, make sure you understand what benefit you're going to get from it. And we've actually seen systems where we've taken accumulators out and sped them up. So not every application can be energy efficient or more energy efficient just by adding an accumulator. So be cautious of that before determining you just want to put an accumulator on a system. Accumulators can absorb volume of oil for thermal expansion. So that can be very important on certain systems. And again, in this instance, that thermal expansion might be on an actuator. So you could have an accumulator on a working port for that reason. You can use accumulators in case of power outages for reserving energy for shutting down a machine. There are machines that could be in a dangerous position if power were lost, and accumulators can be used to return them back to a safe point. Reserve energy for security on hydraulic vehicle barriers and blast doors. So if you lost power, in a secure area. You still want to be able to close the blast doors maybe, and as well as for anti-terrorist vehicle barriers. If you lost power, you still want to be able to raise those barriers up and maybe even down and up a few times while the accumulator does not need to be recharged. Now, the difference that we often run into here is that these types of applications do not have an automatic safety bleed down, whereas most accumulator systems, you want, when you shut the machine off, you want the accumulators to dissipate their energy so that somebody doesn't mistakenly cause some type of unintended action by operating a valve or by taking a valve off and having, 20 gallon of oil just blow onto high pressure oil, blow onto somebody. So a lot of machines will have an automatic safety bleed down, but in these cases, you're going to work against that because you need the oil to be in that reserve to be able to take care of whatever it is you need to move for safety or security. So just be aware whenever you're designing circuits or working on circuits, not every safety type of system will bleed down. You can also use accumulators for surge suppression. They can be on pressure lines to smooth out the pulsation of piston shots from piston pumps. It really helps to quiet the noise down coming out of that piston pump. They can be on actuator ports to absorb shock. We see that on forklift mass cylinders as well as on rock crushers. So they're like shock absorbers. Mass cylinders on forklifts, you think about it, they go over a 3-inch concrete lip with a full load on. The shock load that goes into that hydraulic system is incredible. And so forklift cylinders without any type of accumulator on them can be very hard to keep seals in them. And so just a little bit of an accumulator on there can make a world of difference. Accumulators can be used on return lines to eliminate decompression or water hammer. And also there are times when you just need to absorb some higher than acceptable back pressure. And so you can put a low pressure accumulator on there and it will absorb a certain amount of oil and then let it dissipate back to tank over time. And maybe it just requires 3 or 4 seconds even to eliminate back pressure issues. So a little bit on repair kits. Most repair kits are interchangeable. What you need to know whenever you're ordering repair kits is the size, the material, what pressure is your accumulator, and whether it's top or bottom repair. Some safety tips to know, practice, and live by. An accumulator may still have dangerously high gas pressure even though the hydraulic gauge reads 0. Before servicing an accumulator, make sure all the gas pressure has been released. So an accumulator that's taken off in a system, maybe it's sent out for repair. They thought the accumulator was bad, but maybe it still has 1,000 psi of nitrogen gas in it. Before anybody works on that accumulator, they have to make sure they know what they're doing and that the gas is released so that all energy is dissipated. I only use inert gas such as nitrogen. Compressed air mixed with oil is lethal at high pressures. If you want to check that out, you can probably Google like death by accumulator, as well as OSHA investigations on accumulators. There's been walls of buildings and people have been killed by using the wrong gas in accumulators. When servicing a machine, look for accumulators and make sure they're locked out or completely drained of hydraulic pressure. So you might be working on one end of the machine, but if there's an accumulator on the other end and it's feeding where you're at, you want to make sure you've got that energy under control. Do not transport fully charged accumulators unless they are approved for transport. You see a lot of things happening. You build it one place, ship it another, and it's not always legal to be shipping fully charged accumulators. Secure accumulators properly with specified or specifically designed clamping systems. So you don't want to just have them, half half secure. You want to completely secure that accumulator with proper brackets and base mounts. When a hydraulic fluid is drained from the accumulator, the precharge gas pressure remains. It's energy that must be isolated or removed before any service is done. And also be aware that some cylinders have accumulators built into them. You don't even know it until you begin to take things apart. Sometimes there's a telltale sign that threads might be tighter than they should be. That's because maybe there's some energy in there that is stored, and by you taking that cap off, it's going to blow loose uncontrolled. And there have been people that have been killed by taking caps off of piston accumulators. So you just want to make sure if anything isn't right, make sure you know what you're dealing with. There's a lot more that we could talk about with accumulators. This is intended to be an introduction to accumulators. There are many do's and don'ts to sizing, selecting, installing, and maintaining accumulators. Accumulator safety, sizing, and selection are topics that need to be understood before recommending and purchasing accumulators. So separate training is available for this. You can contact us with questions pertaining to any of this, and just like to say thank you for this opportunity. Accumulators, I think, are not always as understood as we would hope they are. I think there's a lot of opportunity for accumulators to work or to make other systems work better than they currently do, but you need to understand and properly choose and maintain systems that have accumulators on them. So again,